Exploring Life. Chapter 17, Evidence of Evolution. Part 2. It might seem like Hardy Weinberg's model overlooks humans, since we are now undeniably one of the forces guiding evolution. Humbly, we call this influence artificial selection. Artificial selection is the process of breeding organisms for specific traits, guided by human choices rather than natural environmental pressures. It's more than just a tool for creating new breeds or crops, it's a working model, at minimum, of evolution. It follows the same basic rules: variation, heritability, and differential reproduction. By watching how traits change across generations under artificial selection, we get a front-row seat to evolution in action, just with a human hand guiding the process instead of nature. Selective breeding is the mechanism behind artificial selection. Humans choose which individuals will reproduce based on desired traits, like size, behavior, or productivity. This process can lead to dramatic changes in a population over just a few generations, resulting in new breeds or varieties that didn't exist in nature. In many cases, the original wild-type organisms are hard or even impossible to recognize. Just compare the Chihuahua to the wolf, or a wild carrot to the ones you find in grocery stores. The wild carrot is an herb with a small white root that historically contained chemicals capable of inducing miscarriage and was used in some cultures for that purpose. In contrast, the modern domesticated carrot has a large, bright orange root rich in sugars and nutrients, lacking those toxic compounds. Resistance development refers to the evolution of organisms in response to human-introduced factors. Insects can develop resistance to pesticides, making chemical control less effective over time. Most alarmingly, bacteria can evolve resistance to antibiotics, leading to so-called superbugs that are much harder to treat. In fact, antibiotic-resistant infections cause more deaths annually in the United States than traffic accidents, highlighting the serious public health threat posed by this ongoing evolutionary arms race. Resistance development can also enable organisms to withstand pollution and toxins caused by human activities, allowing them to survive and even thrive in contaminated environments. Human pressures like habitat loss and poaching don't just threaten species, they can reshape how they evolve. In fragmented habitats, some animals adapt by becoming smaller or altering behaviors to fit urban environments. Poaching, especially for traits like large tusks, can drive evolutionary shifts in timing, behavior, or physical traits. During the Mozambican Civil War, 1977 to 1992, about 90% of elephants were killed for ivory. Tuskless females had a survival advantage, and their numbers rose from 20% to over 50%. As you've learned, this reflects a dramatic shift in allele frequencies for tusk development. Now it's your turn to reflect. Think back on everything we've explored: the fossils, embryology, DNA, anatomy, living fossils, and more. Which piece of evidence for evolution do you find the most compelling, and why? What stands out to you about it? Is it something visual, measurable, or perhaps something that challenged how you originally thought about life on Earth? Use this activity to connect scientific evidence to your own perspective and deepen your understanding of what evolution really means, and how we know it's real. We've spent the last few lectures diving deep into the mechanisms of evolution, how traits change, how populations shift, and how evidence supports it all. Now, it's time to return to planet Earth's story and see how those mechanisms set the stage for an explosion of life's diversity and complexity. What made this leap possible? A trio of biological game changers. Oxygenation of the atmosphere, the evolution of sexual reproduction, and the emergence of multicellularity. The Cambrian explosion refers to a rapid diversification of life that occurred around 500 million years ago. In just 10 to 20 million years, a blink in geological time, nearly all major animal groups emerged. Creatures with eyes, shells, skeletons, and new modes of movement appeared, transforming the biosphere. This was the moment when complex ecosystems took off, laying the foundations for modern animal life. What caused the Cambrian explosion? While no single cause has been confirmed, the most widely accepted explanation points to a combination of oxygenation and ozone formation, both driven by early photosynthetic life. After billions of years of microbial activity, oxygen levels in Earth's atmosphere stabilized at higher levels. This allowed for the formation of the ozone layer, which shielded the planet from harmful UV radiation. With more oxygen available for metabolism and UV protection finally in place, life could safely expand into shallow waters and eventually onto land. And it did rapidly. Complex multicellular organisms diversified in a burst of evolutionary creativity, setting the stage for the rich ecosystems we know today. This image presents a visual timeline of Earth's history, highlighting major milestones in the evolution of life. Up to this point in the course, we've focused on the earlier portion of Earth's history, shown here in gray, which spans the majority of the timeline and includes key events like the oxygenation of the atmosphere, the emergence of sexual reproduction, and the rise of multicellularity, all marked on a billion-year scale. Now, we shift our focus to the more recent and dynamic chapter, a relatively brief segment of time when complex multicellular organisms began to dominate Earth's ecosystems. Two major, interconnected forces have driven evolutionary change on a planetary scale: climate change and plate tectonics. Throughout Earth's history, climate change has played a powerful role in shaping evolution. Shifts in temperature, sea levels, and weather patterns transformed ecosystems and forced organisms to adapt, migrate, or go extinct. One of the key drivers behind long-term climate change is plate tectonics. Earth's tectonic plates move only a few centimeters per year, but over millions of years, they've completely reshaped continents, oceans, and ecosystems. As land masses drift and collide, ocean currents shift, climates transform, and new habitats emerge, creating both challenges and opportunities that guide the course of evolution. Over Earth's history, the movement of tectonic plates, which continues to this day, has caused continents to drift, collide, and occasionally merge into massive landmasses called supercontinents. One of the most famous examples is Pangaea, which formed around 335 million years ago, bringing nearly all land on Earth together into a single, giant continent. Eventually, Pangaea began to break apart, splitting into two major landmasses, Gondwana in the south and Laurasia in the north. This breakup dramatically reshaped Earth's geography and climate, and set the stage for new evolutionary paths, as populations became geographically isolated from one another. As tectonic plates shift, they reshape the continents and oceans, altering global climate patterns and redirecting ocean currents. These changes can create massive environmental shifts. Some areas become colder or drier, others more tropical or flooded. Ecosystems are disrupted, habitats lost or transformed. For living organisms, this means both challenges and opportunities. Populations must adapt, migrate, or face extinction. And those that survive often evolve new traits in response to the changing world around them. In this way, Earth's restless geology has been a constant force behind the evolution of life. Ice ages are long-term periods in Earth's history when large ice sheets persist year-round near the poles. We're currently in an ice age that began about 2.6 million years ago. This global cooling trend likely began as a result of plate tectonics. As continents drifted, they altered ocean currents and atmospheric circulation, which gradually changed Earth's climate. Importantly, ice ages are not uniformly frozen. They're marked by alternating glacial periods. Within an ice age, Earth's climate shifts between colder glacial periods and warmer interglacial periods. These fluctuations are largely driven by Milankovitch cycles, cyclical changes in Earth's orbit, axial tilt, and wobble that influence how sunlight is distributed across the planet, especially at higher latitudes. Right now, we're in a relatively stable interglacial period. The most recent glacial phase lasted nearly 100,000 years and ended around 12,000 years ago, just as early human civilizations were beginning to emerge. And if you're wondering why the Ice Age movie franchise skipped orbital dynamics and focused on continental drift, well, just picture the sloth trying to explain axial precession. Honestly, they probably made the right call. This illustration shows the distribution of fossils found on today's continents. Identical or closely related fossils appear on land masses now separated by oceans, reflecting how species were once distributed across connected land areas. Around 250 million years ago, these continents were part of the ancient supercontinents Laurasia and Gondwana, which helps explain the fossil patterns we observe today. Throughout Earth's history, life has flourished, but it has also faced devastating setbacks. A mass extinction is a rapid and widespread loss of biodiversity, where a large percentage of species disappear in a relatively short time. In the last 500 million years, Earth has experienced at least 5 major mass extinctions, each resulting in the loss of over 50% of all species. These events reshaped ecosystems, ended entire lineages, and opened up new evolutionary paths for the survivors. Around 250 million years ago, Earth experienced the most devastating extinction event in its history, the Permian mass extinction. It wiped out an estimated 96% of all species, both in the oceans and on land, earning it the nickname the Great Dying. The likely cause? Massive volcanic eruptions that released enormous amounts of gas and ash, leading to climate shifts, ocean acidification, and widespread habitat collapse. This extinction reshaped the course of life on Earth and cleared the way for the rise of new groups, including the ancestors of dinosaurs. About 65 million years ago, Earth was struck by a catastrophic event, the Cretaceous mass extinction. It marked the end of the age of dinosaurs, wiping out nearly all of them, except for one surviving group, the birds. The leading theory points to a massive asteroid impact, which triggered wildfires, sent debris into the atmosphere, blocked sunlight, and drastically altered the climate. This sudden environmental collapse cleared the way for mammals to rise, and eventually, for humans to appear. We use mass extinction events to help construct the geological timescale, essentially Earth's calendar, dividing its 4.5 billion year history into eons, eras, periods, and epochs, much like we divide our own calendar into seasons, months, weeks, and days. Each division marks a major shift in the planet's climate, geography, and life. These catastrophic events close one biological chapter and open another, helping us trace the story of evolution across the full span of Earth's history. This graph shows extinction events throughout Earth's history. The x-axis represents geological time in millions of years, while the y-axis indicates the percentage of species lost. The sharp spikes highlight major mass extinctions, periods when biodiversity dropped dramatically in a short time. These extinction events also mark boundaries on the geological timescale, reflected in the color-coded divisions of Earth's major periods. Over 99% of all species that have ever lived are now extinct. Extinction isn't a failure, it's part of life's rhythm on a dynamic planet. Today, scientists suggest we may be living through a sixth mass extinction, often called the Holocene extinction. While human activity is clearly accelerating the pace of change, there's also an intriguing idea: this event might have begun before we arrived. As other dominant species disappeared, early humans found open ecological space, room to expand, adapt, and eventually rise to global dominance. So rather than being the initial cause of this extinction, we may actually be its beneficiaries, our very emergence tied to the gaps it left behind. Now it's time to pause and check your understanding. This isn't a test, it's a chance to reflect. Take a moment to think about which ideas felt clear, and which ones you might want to revisit. Understanding evolution is about seeing the big picture and the processes that connect it all.